Hello everyone, welcome back to General Chemistry Laboratory. Today the topic of our discussion is synthesis or one might call it preparation of a copper coordination compound. This experiment is the one hopefully you will get to do in person in the lab. It's part one of a multi-part experiment titled Synthesis and Analysis of a Coordination Compound. So today we're talking about how to make this substance and calculations associated with this experiment. And following portions of the experiment will have to do with analyzing this compound for mass percent of its components. But first let's talk about the synthesis. So this compound is a purple solid. I have some from a previous semester here in the vial so you can see what it looks like, what it should look like when you're done. So each of you will be provided with a glass vial with a cork stopper like you're seeing here, and you'll be able to make this compound, and after drying it on a paper towel, you're going to place it in this vial and put it in your drawer for the following week when you will actually analyze it. To make this compound, there are two starting materials used. First starting material is a solid. It's light blue in color. The chemical formula of it is CuSO4 5H2O, and the chemical name is copper sulfate pentahydrate. Note here there's 5 waters in the substance, and there's a dot separating copper sulfate unit from 5 water molecules. What does that mean? Well, there are several things that you need to know. First, this means that the solid material does contain 5 water molecules per 1 copper sulfate unit. It may seem weird that water is present in the solid, but in fact in chemistry it's quite common for solids to contain water. Such substances are called hydrates. Pentahydrate in the name corresponds to 5 water molecules present in this particular compound. The dot here represents a special type of chemical bonding that exists between copper sulfate and water. Coordination bond is characterized by the fact that it's a fairly weak type of bond, and water in general can be easily removed from the solid by simply heating it. But in this case, you're going to use this substance as your starting material. You will be directed to weigh a specific amount of it and place it in a beaker and then dissolve in water. And then you're going to measure the second reagent, which is ammonia. This reagent, unlike this first one, which originally starts as a solid and only ends up aqueous after it's dissolved in water during the experiment, unlike that one, ammonia is originally present as aqueous solution. Couple of things we need to talk about as far as ammonia. First of all, the solution used in this particular experiment is concentrated ammonia, whose molar concentration is equal 15 moles of ammonia per liter. Second of all, one thing you need to know is ammonia is originally, I would say, is a gas. It's a gaseous compound. But here you see it's NH3 aqueous. What you need to know is that ammonia is extremely well soluble in water, and when it dissolves in water it produces a substance called ammonium hydroxide. We talked about ammonium hydroxide when we discussed identification of a compound experiment. Back then I told you that when ammonia and water react they produce ammonium hydroxide, but ammonium hydroxide is very unstable and quickly breaks down into ammonia and water. So bottom line is, even though technically ammonia is a gas, we often refer to its aqueous solution, which in fact is ammonium hydroxide NH4OH. We frequently refer to a solution of aqueous ammonia hydroxide as simply ammonia. So ammonia and ammonium hydroxide are sort of terms used interchangeably. Keep that in mind. So going back to our chemical equation, we now are looking over to the product side, and as you can see, there are two products. One is liquid water. The second one is that purple material that I showed you. Its chemical formula is shown here. CuNH3,4SO4H2O. The chemical name is tetramine sulfate copper monohydrate. So if you compare the chemical formula of the product to that of this first reactant, you'll notice what is happening as a result of this reaction. First, you'll notice only one water remaining. 5 waters is what we started with in our hydrate. And now, instead of pentahydrate, we have a monohydrate, meaning 1 water. You'll also notice that the other 4 waters have been replaced by 4 ammonia molecules. And that's why it's tetramine copper sulfate monohydrate. And then 4 waters are basically forced out of the molecule. Like I mentioned, the product is purple in color compared to light blue reactants. So when you combine your 2 reactants, you will notice color change very quickly occurring from light blue to purple. When you combine ammonia and copper sulfate, you'll notice that the equation has to be balanced, and there's 4 ammonia molecules needed per 1 copper sulfate pentahydrate unit, and then 1 unit of product is obtained. Why is that important? Well, because in this experiment we're making an emphasis on stoichiometry. So you're going to be looking at limiting reactant calculation, and you will have to find out which reactant is limiting here based on the amounts you yourself use in this experiment. So I'm going to go over those calculations. First, you will have to complete them most likely at home after lab, because precious lab time will be spent starting analysis as soon as you complete the synthesis portion. Typically, we have students do these calculations in class, but this time you're going to do them at home. So hopefully this discussion will help you when you start working on those calculations. I'd like to point out that all these calculations will have to be reflected on so-called supplemental data sheet, which is not in your lab manual. Instead, it will be posted on Canvas as a PDF or Word file, which you will be able to print out, complete the work on it, and then submit it to Canvas. So first task on the supplemental data sheet is to figure out which of the 2 reactants, copper sulfate pentahydrate or ammonia, is limiting reactant. What is limiting reactant? Well, limiting reactant is a reagent, as you know, that's going to run out first. But how do we know which one will run out first? Well, in order to figure that out, we need to find out how many moles of product we can obtain from moles of each of the reactants taken. So first step is to find how many moles of copper sulfate pentahydrate is actually being used in your experiment. You will, like I mentioned, weigh recommended amount of copper sulfate, and you'll record it onto data sheet 1. Make sure to record mass of copper sulfate you use with proper number of significant figures. Remember, our balances weigh to the nearest milligram, so you need to have 3 digits after the decimal for the mass of copper sulfate. The mass will be given approximately in the directions. You can weigh anywhere close to the recommended amount. It doesn't have to be exactly the amount recommended. Anywhere close, a little bit more or a little bit less is fine. Knowing grams of copper sulfate, you will need to convert it to moles of copper sulfate. Remember, there are 5 waters present. These waters are present in the solid, and as such must be included in mole mass calculation. So how would you break it up? I would suggest 1 copper, 1 sulfur, 4 oxygens, and then one easy way to do this is 1 H2O molar mass has molar mass of 18. You have 5 of those, so you would just add 5 times 18 to the mass of molar mass of copper sulfate. Or you can just do like I show here in the notes. These notes will also be posted on Canvas for your reference. So you can just do 1 copper, 1 sulfur, 4 oxygens, and then like I said, 5 moles of water, or 10 moles of H and 5 moles of O. This represents 5 waters. So first step is to find how many moles of copper sulfate pentahydrate was used. And then the second step is to find how many moles of ammonia was used. Now, ammonia is originally a solution. Unlike copper sulfate, which is used as a pure solid, weighed as a pure solid, here your moles of ammonia has to be found in solution. And here we need to use what's called molarity or molar concentration. It is my hope that by the time you come to lab to do this experiment, you will have talked about solutions and ways of expressing their concentration in lecture, and you will be familiar with the notion of molarity or molar concentration. Molarity of ammonia used in this experiment is equal to 15 moles of ammonia per liter of solution. And you will also know from your experiment, from your actual measurement, how many milliliters of ammonia you use, how much of ammonia you measured into your graduated cylinder. And so you will start with milliliters of ammonia. This is a conversion to liters. Remember, 1 liter is equal 1 times 10 to the third milliliters. Milliliters cancel. So at this point we have our volume of ammonia used in liters. And then we multiply this by 15 moles of ammonia per liter. That's molar concentration. As a result, liters of ammonia cancel, and you will find moles of ammonia that was actually used for the reaction. So now that you have moles of both reactants that we used, now it's time to start finding how many moles of product you could get. And this brings me back to the balanced chemical equation, which, by the way, is given in your lab manual, specifically on page 85. So you can use that for reference. Remember, in this particular experiment, there is 1 mole of copper sulfate that's expected to react with 4 moles of ammonia. So in this instance, the ratio is 1 to 4, and that's an important factor. So when considering how many moles of product can be obtained, if we start with moles of copper sulfate and we look at this reactant and the product, hopefully you can see it's 1 mole of copper sulfate producing 1 mole of ammonia of the product. But 4 moles of ammonia produce 1 mole of product. So this 4 moles of ammonia has to be accounted for. How do we account for it? So we have to find, once again, moles of product that would be formed from whatever moles of copper sulfate we found in number 1. And here we use 1-to-1 molar ratio, so you will have to set up your unit cancellation or your dimensional analysis showing how moles of starting material, copper sulfate pentahydrate, is converted to moles of product using 1-to-1 molar ratio, which we saw a minute ago from the equation. Then you're going to find how many moles of ammonia, how many moles of product can be found from moles of ammonia used. So you will have found how many moles of ammonia was measured and used for the reaction. That's what you found in step 2. And then you need to use the balanced equation where, again, 1 mole of product is produced from 4 moles of ammonia. So when setting up your dimensional analysis, finding moles of product, don't forget 1 mole of product is produced by 4 moles of ammonia. Once you will find how many moles of product could be formed by ammonia, then you need to carefully and clearly make a comparison. You want to know which reactant produces fewer moles of product. And that reactant will then run out first and will be considered limiting. Remember on your supplemental data sheet to clearly show units for every parameter you find. There's many moles of different things. So it has to be clear with each number you find what that number represents. Moles of what substance, whether it's reactant, whether it's product, and so on. And then this clear comparison must also be shown. It has to be clear how many moles of product will be expected to be produced by copper sulfate, how many moles of product will be expected to be produced by ammonia, which one is larger, which one is smaller, and which reactant is limiting. The other reactant will then be considered an excess reactant. The other thing on the back of that supplemental data sheet, make sure to fill out both front and back of the supplemental data sheet. Supplemental data sheet in the back, it says must be turned into UT at the end of that period, but will actually be giving you enough time to complete it, but I'll give you an extension on that. On the back of the supplemental data sheet, you'll be finding theoretical yield of the product in grams. So you will start with moles of limiting reactant that you have found previously. You'll convert it to moles of product, and then using chemical formula of the product, you will find how many grams of product is expected. Theoretical yield is typically found in grams. The other type of yield that's typically found in the synthesis procedure is percent yield, which shows the ratio between actual yield and theoretical yield. We will hold on finding actual yield until after product has a chance to dry, and then once product is completely dry, you'll be able to find its actual yield and eventual percent yield. So hopefully this discussion helps you with completing all the needed calculations for synthesis and analysis of this material. In the next video, I'll briefly discuss the procedure.